This presentation is delivered by the Stanford Center for Professional Development.
Today I am joined by a very special guest speaker, Professor Jure Leskovec. Professor Leskovec is an assistant professor of computer science here at Stanford University, where he is a member of both the Info Lab and the Artificial Intelligence Lab. His research focuses on mining and modeling large social and information networks, their evolution and diffusion of information and influence over them. Problems he investigates are motivated by large-scale data, the web, and online media. He has received 6 awards for Best Paper, an ACM KDD Dissertation Award, the Microsoft Research Faculty Fellowship, and has appeared on IEEE Intelligent Systems magazine of AI's Top 10 to Watch. He has authored the Stanford Network Analysis Platform, also known as SNAP, a general-purpose network analysis and graph mining library that easily scales to massive networks with hundreds of millions of nodes and billions of edges. Before joining Stanford, Professor Leskovec spent a year working as a postdoctoral researcher at Cornell University, working with John Kleinberg and Dan Huttenlocher. He completed his PhD in machine learning at Carnegie Mellon University in 2008. Professor Leskovec, thank you for joining us today.
Thank you. Hello, everyone. So thank you for joining us today. So my plan for today is to give you an overview of what my group's research is about, sort of highlight the results, maybe don't go into details of the methods, and sort of many of these examples are cases of how analyzing big data can help gain useful knowledge, and many of these things are also taught in the classes that I teach here at Stanford. So let me start sort of with a general introduction and then slowly dive into little examples of what we have. So basically, if we think what is there going on today online is that sort of we have these diverse online computing applications that range from online social networks to, for example, the whole stack of different online social media and mainstream media sites to virtual worlds and all kinds of communication tools that allow us to communicate with one another, right? So we have these sort of big, huge online computing applications. The other thing that these applications all have in common is that people don't just sort of use them as a static library, but they generate this rich and highly dynamic content and interactions between users and content and the users and users, right? And sort of what this means is that because billions of humans are using these things, is that now we have access to these massive digital traces of human activity, right? Sort of everything we do on the web leaves a trace, and now we can study these traces, right? And because we have billions of humans, we can sort of finally start to model society at large, right? So overall, how I think of my research is that basically the web is the laboratory for studying the pulse of humanity, right? And one way how we can approach sort of this big web-scale data is through using data mining and machine learning to sort of tease out the knowledge and the signal from big data. So if you start saying, okay, so I have this data, how can I first represent it? One common thing all these applications have in common is that this kind of large-scale web interaction data can be nicely modeled as networks, right? So it can be modeled as interaction networks where nodes can represent, let's say, people, and edges or connections between pairs of people represent maybe friendship or communication or something like that, right? So this data can very naturally be viewed as networks. So many other types of data can be viewed as a network, right? Sort of, for example, internet, meaning physical communication, or the autonomous systems level of the internet, they can all be viewed as a graph of nodes and connections between them. Citation networks, meaning either patent citations or scientific citation networks within scientific publications, again, can be viewed as networks. Web graph, right? So web pages and hyperlinks between them, again, is a graph or is a network where nodes are web pages and connections are hyperlinks. Another successful area where sort of analysis of networks has been applied is neuroscience, where now we can think of brain or neurons as networks. Of course, there are also other types of networks. For example, text can be viewed and represented as a giant graph or a network. In systems biology, analysis of networks also is very successful, where now, for example, genes or proteins are represented as nodes, and connections mean that two proteins interact with one another, for example. Software, like software call graphs and so on, again, this can be represented as huge networks. And of course, online, let's say, social or communication networks, email networks, these are all examples of the kinds of network data that only recently has become available for us to analyze and try to understand. So why is all this different is that because sort of if we wanted to work with large-scale interaction data, traditional obstacle was that sort of we could only choose 2 out of these 3 things that I'm listing here, right? So we would like our data to be large-scale, be realistic, and completely mapped. By completely mapped, I mean is that the data we have, of course, is sort of, it doesn't contain missing stuff, right? And traditionally this was very hard to get, but today, because of these online computing applications, social computing and so on, detailed records of activity can be collected through the online world, right? And by this I mean online social networks, different kinds of communication tools, and also, for example, online publication repositories like patents databases, archive, Medline, and so on, right? So all these are now huge databases of somehow linked pieces of content or connections, interactions between humans and content. So another important point to note is that the size of the network data has increased immensely, right? So for example, here I'm listing historically, not even 10 years ago, from sort of size of the networks people were looking at to sort of what was, where the trend is going, right? Sort of the 400 node network was the email network of scientists inside HP Labs here in Palo Alto, right? And then, for example, the next size scale is the 40,000 node email exchange network of a large university from the East Coast. And then, for example, another few orders of magnitude up, you get the friendship network from a online blogging community, all the way up to a 240 million node network that is all the users of Microsoft Instant Messenger. And what is sort of the common theme as you increase the size of the data you are looking at, sort of you can tease out finer and finer signals from the data. So one of sort of the overarching themes of this talk today will be that sort of benefits of working with big data, and in particular patterns or sort of statistics become that otherwise are sort of indistinguishable now become visible. So let me start sort of going more into details and saying, okay, so what will be the 2 parts of the talk? So the 2 parts of the talk will be the following. So the first part of the talk will start asking about what is the structure of networks, right? So how can, for example, how can I reason or understand connections in these networks? And in 2 particular applications that we will look at, one will be how do you predict new links in networks? For example, how do you recommend friends on Facebook? That's a direct application of that. And the second one will be how do you go beyond just recommending people you may know to actually recommending friends versus recommending enemies, right? So I have now 2 types of connections. I have friends, people I trust, and I have negative connections, maybe enemies, people I distrust, and so on. So that will sort of be the first part. And then the second part will be about how do I now reason about processes and dynamics taking place on networks. And in particular, we can think about how does information or disease sort of spread like a virus through the connections of the network. And in particular, what we will look at here is sort of what kind of insights can we get by analyzing the interaction between blogosphere, mainstream media, and Twitter. Sort of how does the online media space work? So that will be the overarching part for the second part of the talk. And to sort of motivate the whole thing a bit, I think there are sort of 2 main reasons why one would want to start networks. And sort of one is more engineering, and the other one is more sort of natural sciencey one, right? So the first thing is pure science motivation, right? We want to build an understanding and theory of how these large social and information systems are organized, right? Sort of what are the underlying principles that lead this kind of organization of these systems, right? What is important to note here that many of these networks, right, they are not engineered, but they emerge. What I mean by that is that there is no central force that would dictate who should connect to whom, right? It's sort of different than the railroad network where somebody decides, we will connect these two vertices, and that's sort of a central body nearly that does that, right? All these systems sort of are emergent, so that's why studying their properties is so much more interesting. And I think the second part that's also very important is how can we use this sort of understanding and theory that we build in the first step to, let's say, build better online applications? Maybe how do we design better services and algorithms? How do we make better predictions to users? How do we better model engagement of users and things like that, right? So sort of those are the two parts or two global reasons why would we want to look at network data, and especially network data from the web. So what I want to talk now is sort of little like 3-4 slide segments about different projects we were doing in our group. And the first thing was sort of a collaboration we had with data science team at Facebook, and it was about trying to predict friends on Facebook, or sort of suggest friends on Facebook, right? So what my goal is, a user logs in and I would like to give them a list of potential friends, and maybe they will click on some of them, and the more they click, sort of the better our algorithm, right? So this is sort of the people you may know feature. And if you start looking at the Facebook data, right, it turns out that 92% of all new friendships on Facebook are friend of a friend. So what do I mean by that is I have a little picture here on the bottom of the slide where U connects to W, right? And W is friend of you, right? So I have this sort of this triad now. I have a triangle of the gray node and the red and the green node, right? So 92% of all the connections Facebooks are between sort of nodes that in the network look like U and W, right? So they have some number of common friends, so their distance in the network is 2. One problem, however, is that even though this is now super easy, right? Just put people together to whom you have common friends. The problem is that an average person, a year ago on Facebook had around 20,000 friends of friends, right? Sort of, I'm trying to suggest you maybe 20 friends out of 20,000 friends of friends that one has. So all in all, this is still a very hard problem. So the way how we will formalize this as a let's say a machine learning problem is the following, right? So our goal is I want to make a recommendation about a list of possible new friends a person will get, right? And the way I will do this is I will use this as a supervised machine learning problem where I will have this kind of training examples, and then based on the training examples, I will try to learn how to separate sort of nodes to which I create edges in the future from nodes for which I don't create edges in the future, right? So we will have this set of nodes, let's call them G, and these are nodes to which people create new friendships in the future. So the way we can think about this is that there is this our node S, which is the node for which we would like to recommend friends, and imagine that I take a snapshot of Facebook network, let's say from May 2011, and then the nodes to which S creates friendships are actually the nodes to which S created friendships from May till today, right? So sort of I hide a bit of my data and pretend I don't see it, and then I want to predict the future, right? So that's how we are thinking about this, right? So now our problem will be the following. Given a node S and a set of labeled nodes, what I call G here, so the nodes to which S created friendships in the future, and sort of the set of red nodes, which are nodes to which S did not create friendships. I want to rank nodes G higher, so I want to give them sort of higher ranking than the red nodes. And the way we will go about this is the following. So the way we will think about this is really the question will be how do I combine everything I know about the users and their interactions and the network structure, right? Because both are important. Our user profiles and sort of habits and interaction history is important to decide who are my strong friends and who are, let's say, my weak friends. But then the network structure is important because sort of one simple intuition is the more friends I have in common, the more likely I am to meet that person and maybe connect to them, right? So the idea, the framework in which we will cast this is random walks. Basically, think of PageRank like random walking on a graph, right? So we will think that there is this random surfer that walks over my graph. He walks around infinitely long, and then at some point in time we stop the time and ask, what is the probability distribution that my random surfer is at one of the nodes, right? So the idea will be, I have this random walker walking around the graph, and I ask how likely is he at any of the nodes. So what we will do is the following. We will have some way to assess the strength of the friendship, right? So we will say some friendships are stronger and some friendships are weaker. I indicate this by the width of the edge here on the picture. And then we will say that this random walker will now walk over these edges of the network with probability proportional to the width of the edge, right? Sort of the walker is more likely to take a strong edge, a fat edge than a thin edge, right? And then what we will do is we will then rank, once the walker has walked on a graph for a long time, we will rank our nodes by probability of visiting, right? So the idea is that I want my proximity, or my sort of this random walk distance from my node S to the other nodes in the network be somehow proportional to the strength of the friendships, and also I want my walker to be more likely to visit green nodes than to visit red nodes. And what is interesting here is actually that one can go and estimate, sort of learn a function that estimates edge strength such that the green nodes are visited more often than the red nodes. Sort of there is a supervised way how we can bias a random walk on the network so that these proximities or these random walk visiting probabilities match our training data. And let me show you how well this works. So for example, we were testing this on Facebook network of Iceland. And the interesting thing was that we were able to correctly predict 8.5 out of 20 persons' new friends, right? So if we would stop the time today, let our algorithm generate a list of 20 friends, then we wait for the person to add 20, we would get 8.5 of them correctly, right? And what is also interesting is that this sort of was a 2x improvement over Facebook's previous people you may know system, right? So sort of this idea of using PageRank-like or personalized PageRank-like random walks combined with the features of the network to measure some kind of proximity or distance between nodes for recommending or ranking of nodes on the network really sort of was the right way to think about this problem in this particular case. And one thing that I should mention, I think these slides will all be available for everyone to see afterwards, and I'm having here in this case on the upper left corner sort of a reference, and the last slide of the deck has references and links to all the papers if anyone wants to go into technical details and see how these things are really done. Okay, so this was sort of the first part, recommending friends. So we are moving on now, and we are proceeding to now sort of putting creature structure on top of our networks, right? We will now distinguish friends from foes, right? So the idea will be that I don't want just view all links as the same, but I want to sort of separate positive from negative links, right? And what I want to understand is sort of how to edge this, we will call them edge signs, right? Pluses and minuses, and the overall network structure interacts. And how should I be thinking about these edge signs? And sort of the application that we will look at is basically edge sign prediction, right? So not just saying who are the people you may know, but basically what do you think of them? Are they your friends or are they your enemies, right? So our setting will be I'm given a network with pluses and minuses on the edges. Can I predict whether a particular edge is a plus or a minus? So let me, before I was making sort of this, in the introduction I was talking about rich data that we have. So for example, here is here is online data that is impossible to collect in sort of some other settings. And basically the idea is that we want networks where people link to one another, but also explicitly tag each relationship with a positive plus or a minus. And here are sort of three online cases where something like this is going on. So the first one is online review website called opinions.com. And here basically people write product reviews, and then there is also this social network where people can tag other people that they trust their product reviews or distrust their product reviews, right? So in this case, trusting someone creates a positive edge, and distrusting someone creates a negative edge. On Wikipedia, there is also an example where people sort of create positive and negative edges to one another. And this means that there is a adminship promotion process where people can get nominated to become administrator, and there is a public election where other people come and say, I vote in support of this candidate becoming an administrator, versus I oppose for the nomination, for the promotion to go through. And again, this creates a signed network with pluses meaning positive votes and minuses meaning negative votes between candidates. And the last network that is that we studied was the Slashdot social network. Slashdot is a sort of very funny or particular technological blog with an interesting user community, where this user community can sort of also has a social network called /.zoo, where people can tag other people as friends or foes. And friend supposedly means you like that person's comments, and foe means you don't like their comments, right? And again, what all these data sets have in common is that you can look at them as signed networks where nodes are people. We have directed edges, which can be positive. Positive means trust, friendship, support, and negative, which means distrust, opposing, enemy. And now we have a sort of a common way to think about these things. Let's think how we can reason about these kinds of structures. So here is sort of something that sociology or social science tells us about networks of positive and negative edges. And this dates back to 1946 by Haider. And one way how to reason about signed networks is to think about the following type of sentences. For example, friend of a friend is my friend, or enemy of my enemy is my friend, or enemy of my friend is my enemy, right? And what these statements really mean, if you sort of translate them to graph theoretic terms, they really talk about triples of connected nodes and what are signs on the edges between those triples. So, for example, here, right, the friend of a friend is my friend is a triad, is a triple of connected edges, connected nodes, where all the signs are pluses, right? And enemy of my enemy is my friend is a second triad here, where you have two common friends having a common enemy. Or you could say, my friend's enemy is also my enemy, right? Sort of these two triads on the left correspond to the three sentences that I have on the top, and then the two other possible labelings of pluses and minuses on these triads are the two pluses and a minus and three minuses. The difference is that on the left, the ones on the left we will call balanced because they are consistent with the intuition above, with the intuition above, and one on the right we will call unbalanced because they are not consistent with this sort of friend of a friend is my friend, right? And the way we can understand the two unbalanced one is, so the first one says I have two friends who don't like each other, right? Sort of I'm the top node, I have two friends I like, but they don't like one another, right? So this is sort of what social scientists say, it's unstable, it's unbalanced, it is bound to, this kind of structure is bound to break. And similar, three enemies, again, sooner or later, two of them will form an alliance and go after the third one, right? So that's sort of one way to think about this. A second way to think about this is to think about this in terms of notion of status or seniority or merit, right? So the idea would be now, if before we were talking about undirected edges, now we will talk about the directed connections. And a directed edge from A to B, which is positive, could, for example, mean that B has higher status than A. So, right, A is saying, oh, you are better than me, right? And similarly, if A gives a negative connection to B, this means that B has lower status than A, right? And basically, based on these directions of signs and links, we can sort of make predictions about how the triangle will be completed. So here, what is interesting is that these two theories, for now they are just theories, give you very different predictions, right? So for example, here I have three cases where sometimes the two theories agree and sometimes they disagree. So here on the left, there is the first simple example, right, where A gives a minus to X, X gives a minus to B. So if I think about what would balance do, it would say, enemy of my enemy is my friend, right? So balance would say that A puts a plus to B, right? So A and B have a common enemy X, so A and B link positively to one another. What status would do would be the following, would say, A says, X has lower status than me, X says, oh, B has even lower status than me, so A has the highest, B has the lowest, so the direction of status points downwards, right? So status theory would say A gives a minus to B. And for example, a similar case is the middle example where now everything that changes directions flipped and signs flipped, and again, balance would say friend of a friend is my friend, and status would say A has the highest status, B has the lowest, so A should give a negative sign to B. And there are also, for example, other cases where, of course, the two theories agree, like in the last case. And to sort of, if you now look at this data that I was talking about, the first thing that sort of pops up, it seems that these social networks, the ones that we looked at, seem to be inherently organized based on status, right? So for example, in this particular case that I'm showing here, where I have two pluses pointing upwards from B all the way to A, and now I ask how will A evaluate B? The A is more likely to give to evaluate B with a minus than to evaluate them with a plus, right? So it's sort of the status or merit or level of achievement type of explanations are much more consistent with the data than this friend of a friend is my friend type of intuition. Another interesting line that follows from this research is that we can predict this friend-foe or trust-distrust relationships with 95% accuracy, which means basically this is illustrated by the figure on the right, where I have a graph and sort of this red edge labeled as a question mark, right? So the prediction task is, what is the sign of that red edge? Is it a positive or is it a negative edge? And we can sort of distinguish or predict with 95% accuracy, while a random guessing would get 50% accuracy. And another sort of surprising thing is that if I have this sort of a simple machine learning model that can do this thing, I can train my model on how people vote and predict how people trust one another, as well as if I would train my model on trust, right? So what this sort of means is that even though these edges have very different meaning, right? They either mean trust or friendship or they are about voting. At the end, people seem to behave using using the same principles. So the same model does equally well on all these data sets and doesn't do any worse than if I would build domain-specific models, which is sort of tells that we seem to have uncovered something that is more general than application-specific. The other thing that I want to sort of point out at the end, at the end, is that another interesting thing is that now we can study how people evaluate one another. And one open question that we are currently trying to understand is illustrated by the graph here that I have, where on the x-axis I'm plotting the status difference between users A and B, right? So this is the data from Wikipedia, where your status, your seniority, your level of achievement is the number of articles you edited in your lifetime, right? Sort of the more articles you edited, the higher your status, right? Sort of a very simple proxy for status. And what I'm plotting is probability of A voting positively on B as a function of their of the difference between their status, right? So difference 0 means that A and B have the same status. Negative difference means that status of A is smaller than the status of B, and the positive difference means that status of A is higher than the status of B. And even though this plot seems to be sort of generally have this kind of decaying trend, which is what we would expect, the interesting thing is that there is this dip at 0, right? So basically what this means is that people are the most negative to people to whom they have similar status, or they have about the same status, right? So it seems that when people evaluate someone who's has higher status than they have, they are very positive, right? That's sort of the left-hand side of the graph. When people evaluate someone who has lower status, they are sort of in this intermediate range, right? There is just sort of this bump on the right-hand side of the graph. But when people are evaluating someone of the same level of seniority, they seem to be the most critical. And the question is, why is that? Okay, so this was sort of the first part of the talk. So in the remaining 15-20 minutes, I want to talk about the second part of the talk, of the research, to give you some flavor of what we are doing and what we are teaching in our classes, which is about how to reason about how information spreads on these online networks. And in particular, what we will look at is we will look in online mainstream and social media, right? And the interesting thing today is that the media online really today covers the whole spectrum, right? We can collect data about traditional mainstream media like TV stations, newspapers, news agencies, sort of blogs, both professional and personal, all the way down to sort of microblogging platforms like Twitter, where people sort of exchange short messages in real time, right? And actually we were collecting this kind of data since 2008 together with a small startup in San Francisco called Spinner. And today, I checked yesterday, we are getting 45 million news articles per day. So we are basically collecting about 25 gigabytes of clean text, textual data per day for the last nearly 3 years. So what this kind of big data allows us to do is to study how the media ecosystem at large. And in particular, what we want to sort of understand is how does the information transmitted by the media interact with our personal social networks, right? So that's sort of the motivation. And the first challenge we need to solve here is to be able to track information as it spreads. And we developed this methodology that we call meme tracker that is able to track on this large scale short textual phrases as they spread between the bloggers or between the mainstream media and so on. So what is the first interesting thing is that these short textual phrases tend to mutate quite a lot. So what I'm showing you here is this is a inclusion graph or relationship between these short textual phrases. This is all one particular phrase from that our algorithm identified from the 2008 U.S. presidential election. This was about sort of a presidential candidate Sarah Palin talking about Obama and telling that he's palling around with terrorists, right? So that was sort of the catchphrase. And here what I'm showing you is each node, each box is a different variant of this palling around with terrorists phrase, and edges represent sort of approximate inclusion relationships. It's almost like a mutation graph or of how this particular piece of information changed over time, right? And we have methods to extract these kinds of phrases, identify them, and put them and find mutational variants. And for example, the first thing that we can do is we can simply plot what is the number of mentions of different phrases over time. And what we get is these sort of very accurate depictions of what was going with media in a particular point in time. So again, sort of the most interesting part in the last 2 years was probably the 2008 U.S. presidential election campaign. And here I'm showing you sort of the time just before the election. And what you can see here is x-axis is time, y-axis is number of mentions per hour of a particular textual phrase or meme that our algorithm identified. And if you remember from there, for example, there was the lipstick on a pig big spike, and there was about the debate about economy, about the fundamentals of our economy being strong, and then a week later the entire economy was in danger. And then, for example, it's interesting here to see all these different ways how Republicans were addressing Democrats about palling around with terrorists. Hey, can I call you Joe, which was sort of Joe as Joe Biden. Then there was this question, who is real Barack Obama, and so on. And for example, the last spike there is the last presidential debate, the televised presidential debate, where sort of there were two big messages that came out of it. And one was sort of this message from Obama about spreading the wealth around, and the other one was the message from candidate McCain that he's not President Bush, right? And what is interesting is that without any supervision, without any manual labor, our algorithms can detect these kinds of things. We can also go sort of further down and ask, okay, so how is news being made? What is the interaction between mainstream media and blogs? And right, for example, what you can do now, you can do these precise measurements where you can sort of identify that on average, blogs tend to trail mainstream media with a 2.5-hour lag, right? So what I'm showing here on the top plot is the time, is x-axis is time, and y-axis is sort of number of mentions, volume. And what you see is that mainstream media tends to peak faster and decay much sooner, while bloggers tend to adopt information or start talking about it with about the same intensity as mainstream media, but then they forget it, or they are stopping much slower, right? This is how you can think about this globally. However, if you look into more details, actually the story is more complex. And this is sort of demonstrated here with this heartbeat-like pattern. What I'm showing here, again, is time versus fraction. So for every hour of the day, I'm asking what fraction of the mentions of a particular phrase came from the blogosphere. So if it goes up, it means there is more mentions on the blogosphere and less on the mainstream media side. If the plot goes down, it's sort of more mentions on the mainstream media side. And what you see is that sort of, and zero time is the time of the peak popularity, sort of time of peak attention. And what you see is that sort of before the peak attention, it's the bloggers that sort of take the attention. And then around peak time, around zero, sort of the volume goes towards the mainstream media, and then again to the blogosphere, which sort of can be explained by saying that we really have two classes of bloggers, right? We have very let's call them agile professional bloggers who are able to very quickly respond to the news. And then we also have personal bloggers, sort of people who get their news in CNN, television stations, things like that, and then blog about these things. So, for example, this is an interesting plot that reveals the relationship between sort of mainstream media blogs, professional blogs, personal blogs. What is also interesting is that now we can start asking and saying, hey, can we model influence different media sites have on popularity of different textual phrases online? And basically what the motivating question here is basically to say, can I model or can I understand if, for example, New York Times mentions a particular phrase, a particular meme, particular piece of information at time t, how many subsequent mentions will this generate at time t plus 1, t plus 2, t plus 3, right? So really the idea is, can I somehow say, if I get New York Times to say something, how much buzz will this create, right? And the way you can think about this is you can think about this as a time series prediction problem, where that I'm trying to demonstrate with the picture here, right? So the idea is I have x-axis is time, y-axis is number of mentions or volume, and imagine that I also know identities of websites. Imagine A, B, and C. These are, let's say, New York Times, CNN, and something else, when they mentioned this particular phrase. And what I would like to do is I would like to estimate what we will call influence functions. These are the three curves below the timeline, right? So, and the idea is that I want to estimate these influence functions in such a way so that at some future point in time, where this vertical line is, the sum of the influences of the website that mentioned the phrase beforehand adds to the current number of mentions on the web, right? So the idea is that when a site mentions a particular piece of news, its influence function starts to run, and then the number of mentions in the future is just the sum of the influences, values of the influence functions appropriately aligned, as the picture shows, right? Summed together, that's my value for that's my prediction for the number of mentions. And it turns out that you can sort of much more accurately than what we were able to do before now predict what will be the popularity of a particular phrase online. That's sort of the first thing. The second interesting thing is that you can start looking at the shape of these influence functions, right? So, and here I'm showing you an example of influence functions for two different types or for two different topics, for sort of topic articles on business or phrases on business and phrases on entertainment. And how to understand these influence functions, the idea is the following, right? So I have 5 different media types: newspapers, professional blogs, TV stations, news agencies, and normal, usual blogs. And the way to understand this is that to say, once a news agency mentions something, then in the same hour there will be, let's say, 60, the y-axis is scaled down, but there will be 60 other sites that will mention this piece of information. And, 1 hour later, there will be about 28 of websites that tend to mention the information and so on. So, for example, what you find for business is that it's news agencies that seem to be the most influential at the beginning, and then their influence drops very quickly. And sort of the overall long-term influence actually it seems to be the bloggers who sort of the blue curve that gets on top there. And the situation is very different, for example, for entertainment stories, where actually it is TV stations and personal blogs who have the highest influence, and then also sort of over time their influence remains quite high. But for example, news agencies don't really play any role, and also newspapers don't seem to be playing much role in the spreading or adoption of entertainment news online, right? So this is, for example, one kind of insight that one can get from analyzing, being able to track information online, analyzing it over long periods of time, and then developing models that are both able to predict how information will become popular, and also to gain these insights about what are kind of roles different media sites play in the diffusion of online information. If I keep going on, sort of the next question is really that this information often spreads over implicit networks. So what I mean here is this used to be a very nice animation where basically my nodes here represent different blogs, and my different colored rectangles represent different types of information, right? So there is a red piece of information and a blue piece of information. All that we really get to see is just when the information appears at the node, right? So I have for every blog I know the time when they wrote about particular piece of information, but I do not know where they got this information from, right? So what I don't get to see are these links that are depicted here. So what I would really like to do is I would like to infer the links. I would like to infer the network over which the stuff spread. And this is sort of my goal, and this is an instance of a much more broader problem of inferring latent social or information networks. So, for example, the same case occurs in if you trace how viruses or diseases propagate, right? So the process that operates on the top of the network is spread of a disease. What you get to observe is times when people got sick. What you don't get to see is who infected whom, right? You don't know the network, so you don't know who infected whom, but you know when people got sick. The question is, can you infer the underlying social network? Or, for example, in viral marketing, this was one of the examples that we also work with the real data. The idea is that people make recommendations to one another and purchases, sort of product purchases propagate through the network. We only get to observe when people make purchases, when people buy products. The question is, can you infer what is the underlying social network over which this recommendation spread? And sort of the interesting fact here is that computationally it turns out that this is doable. So it means we can find near optimal networks in polynomial time, in quadratic time, even though if you think about what is the space of all possible graphs, it's sort of 2 to the n squared, this sort of order of that, right? It's the number of all possible adjacency matrices, right? Sort of even though we have to search this huge space, we can find something that is probably very close to the optimal solution in sort of very short time, in quadratic time, where with the size of the network. And the insight, sort of, if you do this, for example, here is an example of a diffusion network of information between 5,000 news media sites, blogs, blue, and mainstream media in red. And the thing is, we find that this network sort of has this core periphery structure. And here it just looks sort of nice and interesting, but if we zoom in, actually we can get some insights. So here is a zoom in into the network on previous slide, where I have now different media sites. I labeled them, and now, for example, you can see that we have sort of these 3 clusters of media sites. I have the politics on the left, entertainment on the top right, and sort of technology on the bottom right. And what you see now, for example, if I contrast a few things here, is, for example, Huffington Post, right, which is a progressive online blog or online newspaper, right? It's heavily embedded in this political cluster. But, for example, if you then look at Washington Post or Salon.com or maybe Guardian, they are much more on sort of on the edge, which means they also get information from other parts, either from the entertainment side of the network or from the technology side of the network, right? We have sites like Gizmodo and CNET.com and so on that are in this technological part of cluster, right? So by being able to infer these networks, we can again try to understand what are the roles different media sites play in this network of information transmission or diffusion. And the reason why we would also want to do networks is because then sort of the application is for influence maximization. So the idea is that we want to, for example, identify influential nodes in networks, right? So the setting would be, where should I put my information, or who should I advertise to, so that I get these network effects and the information spreads through the network. Or you can look at the flip side of the problem, where you say, how should I monitor my network to detect outbreaks as quickly as possible? So, for example, you could say, I have a water distribution network of a city. There may be diseases spreading through or contamination spreading through. Where should I put my monitoring station so that I detect that there is a contamination in my water distribution network as quickly as possible? And the way we can think about this, sort of both these problems can be thought of about some kind of covering the graph, right? So the idea is that every node has either a set of nodes that it influences, or it somehow has a set of nodes from which it can detect that there was an infection. So now the idea is I want to select a small subset of nodes so that sort of I cover this network. And the interesting thing is sort of this set cover-like problem, again, in general, is NP-hard, but we have a near linear time algorithm that again probably can find solutions that are close to the optimal. By close, I mean in practice they are at 95% of this optimal NP-hard solution to compute. And what I'm showing you here is a particular visualization of real data where we have where every dot is a blog, and this is the result of our algorithm that we say, okay, I want to suggest you a set of blogs to read so that you are most up to date, right? So that whenever there is a big information outbreak, you get to learn about it as quickly as possible. And these are sort of the numbered nodes here are the nodes that our algorithm selects so that you quickly capture information from various parts of the network, as you can see here. So that sort of concludes like, let's say, little vignettes about the types of research that my group is doing, and sort of types of problems that we also investigate in our classes, both from the technical point of view of how do you work with big data to the more theoretical point of view of how do you go and actually reason about these systems, and how can you abstract the data out and think about them as networks. So just to wrap up, let me say the following things, right? Sort of one big motivation for all these things is really trying to understand why are networks, let's say social and information systems, organized the way they are, right? And sort of only recently these basic properties have been we were able to observe them on a large scale, right? And here are very nice connections with social sciences and also with sort of physics, complex systems, study of complex systems in physics, right? And many times, many intuitions from these fields are confirmed, but other times they are also not confirmed, or they are called in questions, and new theories need to be developed. And in particular, we try to understand these kinds of things through tractable models, both to be able to make useful predictions or to be able to analyze these models, to have intuition and understanding. And then I think one of the benefits of overall is working with big data, right? So that we can observe structures, make measurements and characterizations that otherwise are basically impossible to do due to the noise in the data. So just to say, what are some of the current research projects that we have in the group? So the first thing, for example, is the understanding how does information spread through networks, and in particular, where, when, and what piece of information will create a big cascade. Right? The idea here is really where should I tap my network to get the effects I want? Maybe for marketing, maybe for evolving the social network in the future. For example, if I'm a social network administrator or an operator, how could I sort of steer or grow the evolution of my community in the right direction? Or sort of what are the metrics or indicators that I should improve for my network to survive longer? Here actually we have some very interesting results where we can, with like 85% accuracy, predict whether a particular online social community will die in the next year or not, right? So there are structural indicators that tell me whether this is healthy community or is it going to die out, right? And sort of the last connection is with all this work with positive and negative edges in networks, about interaction between trust and distrust and the network structure. So this concludes my talk. I thank you everyone for listening. The last thing I will say, everything that I talked about today has actually been published, and the references and links to papers are on the last slide of the deck. I think now Michelle will take over, and then I'll be happy to take questions.
Thank you so much, Professor Leskovec, for participating in the presentation today and sharing your research with our audience. We're going to go ahead and respond to audience questions, and while we collect the questions from the queue, I'm going to take a few minutes to share some of the information about a new certificate program that we're offering in the area of data mining and knowledge discovery techniques, extracting information from large data sets such as the web, social network graphs, and large document repositories. Mining Massive Datasets is our newest graduate certificate program and is offered by the Computer Science Department and made available through the Stanford Center for Professional Development. This certificate can be earned by successfully completing 4 courses totaling 13 units of graduate credit, resulting in a certificate award signed by the Computer Science Department and the School of Engineering. 2 of the courses that contribute to this graduate certificate program are available online during the autumn quarter: Social and Information Network Analysis and Machine Learning. The enrollment period for autumn quarter is now open, so please go to our website, scpd.stanford.edu, and submit your application for enrollment today. The Stanford Center for Professional Development serves as a bridge between Stanford University and industry, offering academic and professional education courses and programs to meet the career-long education needs of engineers, scientists, technology professionals, managers, and executives. Our center has been a part of the Silicon Valley, extending Stanford education for over 50 years, and based on customer feedback, having access to Stanford-level education is critical to maintaining a competitive position in the marketplace. Stanford Center for Professional Development offers approximately 200 graduate courses each year that can be taken online for academic credit without having to be formally admitted to a degree program. We also offer course bundles or graduate certificates comprised of 3 to 5 courses and a focused, guided curriculum of study, which offers not only Stanford University graduate credit, but also an in-depth subject-specific knowledge. We also extend master's degrees to industry through our honors cooperative program. Candidates must apply like any other graduate student, and if admitted, can pursue their degree on a part-time basis over the course of 5 years. And up to 18 units of graduate credit earned under the non-degree option may later be applied toward a master's degree if admitted. We also offer the option to audit courses, allowing you to update your knowledge without homework, exams, or interaction with the teaching staff. The enrollment period for autumn quarter is currently open and will remain active until Wednesday, September 21st. If you're interested in enrolling in any of the graduate courses offered through the Stanford Center for Professional Development, you must do so online through our website at scpd.stanford.edu. Tuition is determined by SCPD company membership and non-membership. And if you are unsure about whether your company has a membership with our center or would like to learn more about the benefits available to member companies, I would encourage you to contact us. I'd like to take a moment to highlight an upcoming webinar that we have scheduled for next Wednesday, August 24th at 9 a.m. It's on the topic of strategic innovation, the power of design thinking in business. And in this live webinar, Professor Bill Burnett of the Stanford University Design Group, along with Carl Spetzler, CEO of SDG, will talk about how successful companies incorporate design thinking into their business processes to increase their bottom line. And before we take the questions, which we'll do in just a second, I just want to take one opportunity to conduct our final poll in this webinar, trying to get a sense of if you could indicate your level of interest in this new graduate certificate program in Mining Massive Datasets. While you're entering a response, I'd like to go ahead and have our speaker take any questions that we have.
Okay, thanks for the questions. So we collected them, and I will just go through and try to answer them. So there was a question about what an edge sign is, right? So as I was saying, a sign is a plus or a minus, and it's sort of application specific, right? Plus can mean you are my friend, and minus negative edge sign means you are my enemy. And similar, then the question was about what is used as indication of trust, right? Sort of in our study, we sort of considered this as simply as binary labels, right? Sort of the indication of trust is defined by opinions, right? Sort of in all these applications, you cannot link to someone unless you say what is the sign of your link, whether that's a positive or a negative link, right? So in this respect, we didn't make any decisions which links are positive and which ones are negative. This was done by the users of these online applications, right? So I think that's important to know that every edge here, the sign was not inferred, but there was a ground truth, and that ground truth was selected by the user, right? It's almost like when you create an edge, like if you think about voting, right? There is no way for you to vote neutral. You either have to vote for or against. Also, there was a question about what kind of data is available there. So in terms of data, we have a website called snap.stanford.edu where we both give away our library, and we also give away about 60 different large online social and information networks and so on. So there is quite a lot of publicly available online data. We also give away our social media news articles data from 2008 at a website called mimtracker.org. Again, linked off the snap.stanford.edu. So if you go to my web page, there is a link to code and data, and for example, that's I think currently the largest online repository of large-scale online social network data. There was also a question about what works and what doesn't, right? I think what is fascinating with study of networks is that sort of different intuitions, sometimes contradictory, can be sometimes right and sometimes wrong. And I think this is really the interesting part. So the problems here is how to identify interesting structures, or how to develop metrics or things to compute in order to understand what is going with the underlying systems. So many times the way I see our research is really about, we are studying this galaxy or this cloud of data that we can, or this cloud which is basically a network. We cannot draw or visualize this network, so we have to come up with different computational techniques that sort of allow us to slice this data in different ways, right? So now my software or programs that we build or analysis that we build is really like a telescope for looking in this data. So that's sort of the way I tend to think about. So there was also a question about how we choose these phrases that we track, these sentences or whatever. So the way we do this is to actually look at the text that appears inside quotation marks. So that's sort of our starting point. So we go through the documents and extract everything that appears in quotation marks, right? So quote, something, end of quote. And based on this, that's sort of like our seed set, and then we take sort of substrings of those kinds of phrases and again search through the text. But the main source of these textual phrases is stuff that, or sort of text phrases that appear in quotation marks. And then we have algorithms that sort of put mutational variants together and so on. The other thing, the question was also, so there is a question about different types of algorithms that are sort of not data mining algorithms that are not machine learning, right? Sort of what people today understand as machine learning is sort of the cases where you have where you can do supervised machine learning, which means where you have ground truth labels, right? So where you have some labeled data so that you can learn how to predict those labels. In many cases, you don't have such data, so you have to use something else, right? So, for example, in our data mining class, only about maybe a third of the class is devoted to supervised machine learning, and the rest is devoted to unsupervised methods like clustering, dimensionality reduction, ways how to quickly compute or count different things, how to find pairs of similar sets of items without needing to compare everything to everything. We talk about how to detect communities or dense clusters in networks. We talk about how to compute page rank or some kind of node importances on big graphs, how to detect spam online, and things like that. So really there is much more to data mining than sort of just machine learning, even though machine learning is a sort of a central part of it. So there is more than that. There was a question about Snap as comparing to other online network analysis libraries like Payek or Gephi. The difference is the following. So Snap is purely written in C++. It has no front-end user interface. It's available under the BSD license, but it can crunch networks of hundreds of millions of nodes, no problem. So the difference is really that Snap is for serious C++ programmers, while both Payek and Gephi are more visualization tools that can load in a network of 1,000 nodes that you can draw, right? Sort of Snap, the idea for Snap is to work with the networks that are bigger than the number of pixels you have on your screen. So there is no hope for you to visualize it. So you have to computationally analyze it. There are also sort of questions about particular applications. For example, there was a question about music industry, how this data can be utilized. There were also, I think, questions from other types of applications. So I'll just try to answer them in the same time. So I think there are different ways how data mining can be utilized. So one obvious way is making better recommendations, either recommendations about people you may know, recommendations about songs that you may like, and things like that, right? Sort of improving user experience. So that is sort of one side of things. But I think the other side of things is also that's very important, is on the analytics side, right? So how to understand user adoption, how to run experiments and try to come up with success metrics, trying to understand how sort of doing some kind of analysis of logs online, trying to see how users are using the site, how are they, what kinds of things are they sharing and what kinds of things are they not sharing, and so on. So I think there are sort of two sides to the thing. One is understanding analytics, building metrics, tools to analyze data to understand what's going on our websites or properties. And the other side is sort of using these insights to be able to build better recommendation algorithms for songs, friends, and things like that. There is a very interesting question about the meme tracker and about sort of convergence of different memes. Actually, we were looking. We don't yet have a very good answer. We see that sort of over time there are more and more variants or mutations of the same piece of information. However, usually there is one that takes over. And we are studying this currently using Twitter data, where what we want to understand is use of hashtags, right? Sort of people label their tweets with a hashtag, and these hashtags are invented by the user community, right? So there is no external force that would say, oh, because Michael Jackson died, this is the hashtag you should be using, and don't use these other hashtags, right? Sort of, but over time it seems that there is one hashtag that the user community converges to. And we are collaborating now with Twitter to be able to do these kinds of analysis. And for example, one interesting nugget right now is that we did the experiment where we were trying to see how much information that appears in the Twitter can be explained because of the Twitter, let's call it social network, right? So that how much information that people say could they have learned from their neighbors, the people they track. And we find that only about 60% of information in the networks can be explained by the diffusion or by the spreading of the network of the information through network, and the remaining 60% just appears at the nodes out of the blue. And the interesting question here is really what explains this 40%? Where are people getting this remaining 40% of information, even like hashtags that are intrinsic to the Twitter network? Maybe it's through trending topics, maybe it's through search, maybe it's through some other kinds of media. So the difference between data mining and machine learning, it's sort of more, in some sense, philosophical, but I would say the following thing. Data mining is you could also call it's knowledge discovery from data, right? So it's a very broad topic, and one subset of this is also sort of machine learning approaches to be able to extract useful knowledge from data, right? So I think of data mining as a broader term. The other thing I think that's important is to also say about there is a bit different focus, right? So for example, if statistics is all about statistical models and not so much about computation, machine learning is more about how do you compute and how do you make your models work, while data mining is in some sense all about computation, right? If you cannot compute your model over the data you have, then the model can be really good, but still it's useless for you, right? So I think there is also this focus in terms of how much data plays importance, and as we will see in data mining, many times there is so much data that even simple, carefully crafted models and approaches do really well. So there is lots of power in the data. I think this sort of answers pretty much all the questions that we sort of collected together in bundles. If there is anything else, we'll be able to answer them by typing to you.
Okay, great. Thank you very much. So today's presentation has been recorded, and we'll be sending out a link to this recorded session to everyone who is registered. We do plan to finish responding to any of your questions that are remaining in the queue, so feel free to stay online, and we'll go ahead and respond to anyone who has not had their question answered yet. If you wish to print out a PDF of the slide deck that was used today, you can go ahead up to the handouts icon in the upper right corner of this window frame, and you can go ahead and print those out. Thank you very much for joining us today.